Okay, this is where it really gets exciting. Chapter 11.5, Probability with the Fundamental Counting Principle, Permutations, and Combinations. In other words, we're going to put together everything we've talked about in Chapter 11 so far to help us solve some probability problems. Let's start with this one. Powerball is a multi-stage lottery played in most U.S. states. It is the first lottery game to randomly draw numbers from 2 drums. The game is set up so that each player chooses 5 different numbers from 1 to 59 and 1 Powerball numbered from 1 to 35. Twice per week, 5 white balls are drawn randomly from a drum with 59 white balls numbered 1 to 59. And then 1 red Powerball is drawn randomly from a drum with 35 red balls numbered 1 to 35. A player wins the jackpot by matching all 5 numbers drawn from the white balls in any order. Here we go. In any order. And matching the number on the red Powerball. With one $2 Powerball ticket, what is the probability of winning the jackpot? So we're going to use our basic probability idea that the probability of winning the jackpot would be the number of ways you get a winning ticket over the total number of possible tickets that's out there, right? That could be selected. Okay? And because the order doesn't matter, this is a combination problem. So what we need to do first, let's talk about the denominators first, right? The denominator is just the total number of possible combinations. And like we said, combinations. So because there are, starting with the white balls, 59 white balls, right? And I need to choose 5 of them. That's our 59. Choose 5, which would be, right, 59 factorial over 5 factorial times 54 factorial. Remember our formula for n choose r is n factorial over r factorial over n minus r factorial. Or we just have this button on our calculator, right? So let me pull out my calculator here and see what this is. Okay, 59 combinations taken 5 at a time. That is 5006386, or in other words, 5,006,386 different ways you can choose 5 numbers out of 59 numbers. Now we need to talk about how many ways we can get a red ball. Well, because there are 35 red balls to choose from and we want 1 of them, that's 35 choose 1. You might notice if you put that in your calculator, you're going to get just 35. Because think about that. If there's 35 balls and you're going to choose 1, how many ways can you choose 1? 35 different ways. There's 35 balls. You could have chosen 1 or 10 or 12 or 34 or 2 or 3, right? 35 different ways. So our denominator, the total number of possible combinations, so let's find the probability that we win, is going to be, I'm going to go back just to make a comment to help us and write this like this, right? Our fundamental counting principle says we need to multiply these things together. If I know there's this many ways that I can choose a white ball, and this many ways I can choose a red ball. The fundamental counting principle tells me then the total number of ways I can choose the white balls with the red ball. I multiply the options. Okay, now the numerator is the number of ways of winning the jackpot, which that means there's 5 white balls drawn. To have won those 5 white balls, you need to choose all 5 of your balls from that group of 5 that's the winning numbers. Okay, now again, if you put this in your calculator, you notice that it's 1. Plus, you need to choose the 1 red ball that is the winning ball. There's 1 right there, and you've got to choose that 1. Here's 5 that are winning balls. You have to choose those 5. This is 1, this is 1. Again, if we think about that for a second, then, oh yeah, there's only one way that you're going to win the Powerball, and that is if you choose the exact numbers that was selected from the balls. So I didn't really have to come up with this format up here. If I just think about, okay, if I buy 1 ticket, there's 1 chance I have to win that. I know my numerator is 1. And let's see what that denominator would be. Let's go back and multiply that by 35. So that is 175. 223,510. So 175,223,510. Now, there's my fraction. If I just want to get an idea of what that number looks like, let me do the division. And I see that the number is too small to even fit on my calculator. So it gives it to me in scientific notation as 5.7 ... e times 10 to the negative 9. So I need to move my decimal 9 places. That would be 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. If I can even fit them in on here. 5, 7, and I'm just going to round 1. So look at this. 0.000000005. Basically 0. The chance of winning the lottery is basically 0. As a matter of fact, it's been calculated that as a healthy, non-smoking 30-year-old is 175,000 times more likely to die than to win the lottery. Okay, that's how small of a chance there is. All right, but let's go back to our problem, just because I want to talk about the format for setting up all of these probabilities. Technically, on this one, I can kind of figure out that numerator is 1. But if I had a different question, like, what if you only get 4 balls that match the winning balls, or other options like that, then I want to talk about the format that all of these set up in. So this says there are 59 white balls. 5 of them are winning balls. That means 54 of them are losing balls, and I'm going to choose 0 of them. Okay, so now here's my 59 balls, and I've chosen 5 of them. Okay, if there's 35 red balls, and 1 of them is the winning one, that means 34 of them are losing ones, and I'm going to choose 0 of them. Every one of these values, if you put it in your calculator, you'll realize they're 1. In other words, how many ways can you not choose the 54 balls? 1. The way that, if you don't get any of them, right? There's 1 way that can happen. But I wanted to put this up just for our future reference to think, this is the way I want to format all of my problems and what I need to think about. I need to think about, oh, how many ways did I choose what was said? And then there's the other option. In this case, the losing balls. And we'll see a problem like this in just a minute. So we'll talk about that a little bit further on the next page. Okay, what about this one down here? Suppose that a person buys 5,000 different Powerball tickets because that person has selected 5,000 different combinations. He just bought 5,000 different numbers. He has the probability of winning. You'd put 5,000 over, notice we got that same denominator. So now that increases your odds quite a bit. Still basically zero. It's 285 in tenths, hundredths, thousands, 10,000s, 100,000s, millions, 10 million. 285 and 10 million. Okay, so still not great odds, and it cost you 5,000 tickets times 2, $10,000 to narrow your odds down that much. But again, that's because up here, he had the one winning ticket, right? He bought one ticket, so he had one chance to win. Here he bought 5,000 tickets, so he had 5,000 of these 175 million combinations. Okay, hopefully that makes sense. If not, let's continue on. And try to, make it more clear. Okay, what about up here? Martha, Lee, Nancy, Paul, and Armando have all been invited to a dinner party. They arrive randomly, and each person arrives at a different time. Okay, so the first couple of problems are going to walk you through the process that, oh, I need to count, up how many ways my denominator can happen, count up my numerator, and then put it together as a probability. Pay close attention to whether you're being asked the number of ways something can happen or the probability that something can happen, right? Two totally different things. So, in how many ways can they arrive? Well, this is basically a lineup. It's saying each person arrives at a different time. So what you're saying is how many different ways can they walk through that door? They could just be lined up outside the door. Okay, that's a permutation. Or, in our case, a fill in the blank one. Right? And because there are 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, there's 5 blanks to fill in. Okay, so there's 5 choices for someone that could arrive first. Any one of those 5 could walk in the door first. But once one of them has come through the door and is at the party, then there's only 4 people left that could come through the door next. And then there's only 3 people left. Once these 3 people are at the party, there's only 2 ways that the next person can arrive, and then 1. So that is 10 times 12, 120. Okay, now it asks, in how many ways can Martha arrive first and Armando last? Well, we've already decided this is a fill in the blank type of counting, right? And if I have some restrictions, I'm going to fill those in first. So Martha arriving first, that means there's one way that can happen. That's if Martha comes through the door first. Okay, no other way it can happen. If Armando arrives last, there's only one way that can happen. If Armando is the last one. That means 2 people are already accounted for where they're going to arrive. So out of the 5 people left, there's only 3 different options that could come in the door second. Okay, and then there's only 2 different options, and then finally just 1 option. So there are 6 different ways that Martha can arrive first and Armando last. Now it asks us to find the probability that Martha will arrive first and Armando will arrive last. So this is the probability that Martha is first and Armando is, we'll say 5th instead of last, a little bit easier to write. Okay, so probabilities, remember, the denominator is always the total number of ways that your problem, the information you're given, can happen. And the numerator is the total number of ways the particular event that you're talking about can happen. Here's the total number of ways they can arrive, right? And here's the number of ways they can arrive under this condition. So that's 1 out of 20, right? The probability that Martha arrives first and Armando last is 1/20. Okay, let's look at this one. A group consists of 4 men and 5 women. 3 people are selected to attend a conference. In how many ways can 3 people be selected from this group? First question is, I have to decide, is this a permutation or a combination? Oh, it's just 3 people going to a conference. The order they get chosen to go in doesn't really matter. Once they're chosen, it's going to be the same group of 3 going. I don't want to count Ned, Fred, and Ed going to the conference as a different group of people as Ed, Ned, and Fred, right? It's still the same 3 people going to the conference. So this is a combination. So now that I know that it's a combination, I've got a formula for that. There's 5 women and 4 men, so that's 9 people altogether. And we're going to choose 3 of them to go to the conference. So I can plug that in to my calculator and get 9, choose 3 to be 84. 84 different ways you can choose 3 people from a group of 9. And how many ways can 3 women be selected from the 5 women? Okay, so we've already decided this is a combination problem. So that's 5, choose 3. Okay, 5, choose 3, that's 10. Now it's asking, find the probability, right, that all 3 are women. Probability's denominator is always the total number of ways that anything can happen, and the numerator is the number of ways your particular event can happen. Okay, so this will simplify. They're both divisible by 2, 5 over 42. Okay, before we leave this problem right here, since it's a combination, let's again make the same comment we made about the lottery one. So technically, I'm going to go over here so I'll have a little more room. If it's just asking me, and it doesn't give me the setup where I've already calculated the individual numbers, okay, here's my format. The denominator is always the total number of ways that anything can happen. Now, if I want to know how many ways I can choose, 3 women from the 5 women, it's 5, choose 3. So really, there you are. That's what we just did down here, except we did them individually. But keep in mind, that's because I chose 3 women, all 3 women. So that really means technically had this going on also. 4, choose 0. Out of the 4 men, I didn't choose any. Because what if the problem asks me, what's the probability that you get 2 women? Right? Then the denominator is the same, of course. But on the numerator, you've got 5, choose 2, and then that other one gets selected from the men. Right? So I just want us to be aware of what's going on these where this other option is 1. It looks like, how come some of them are different? How come sometimes I just put, 1 here and sometimes I use my fundamental counting principle? I always do. It's just this number is 1, 4, choose 0. But it really is always the same format. Okay, I hope that's making sense. All right, let's try again. A player wins a minimum award from a lottery of $150 by correctly matching 3 numbers drawn from white balls, 1 through 56, and matching the number on the gold mega ball, 1 through 46. What's the probability of winning this consolation prize? Okay, so the probability, of winning, we'll say the consolation prize. Yes, first of all, I have to figure out the total number of possible number combinations, right? I know it's a combination because we already talked about with a lottery that your, I just lost my pen again. Let me see if I can bring it back. Okay, that your sorry, that's distracting me. That your the order doesn't matter that you choose these numbers in, right? The order doesn't matter. So the total number of possibilities of getting your white balls, right? Let's see. I think there's a little information missing on this. We're still talking about, you've got 5 balls from the white balls. Yeah, I'm sorry about that. I missed a little bit of information on this question. So we need to know that you choose 5 numbers from the white balls and 1 from the gold ball. So then keeping that in mind, there's 56 balls this time that you're going to choose your 5 from. And using the fundamental counting principle, there's 46 balls this time that you're going to choose 1 from. This looks like Mega Millions. The other one was Powerball. Okay, so here's the total number of ways you can draw a white ball. 5 white balls, out of the 56, times the total number of ways you can pick 1 gold ball out of the 46. But this time, you only match 3 numbers from the white balls. Okay, so there are 5 winning white balls drawn. There's 5 of them, and you selected 3 of those 5 white balls, which means you still had 2 more balls, right? So that leaves you 51 non-winning balls, and you chose 2 of those. Okay? Now, that's the number of ways you got the white balls. And think about this. What that's doing is, let's say the winning numbers you matched were 1, 2, 3. Let's say 1, 2, 3, 4, 5 was the winning numbers, just to make it easy. That's the 5 winning numbers, right? 1, 2, 3, 4, 5. And you had 1, 2, and 3. But you could have had 1, 2, 3, 7, and 9 for your tickets. You could have had 1, 2, 3, 12, and 20 for your tickets. You could have had 1, 2, 3, not 4, because that's a winning one. So let's say 41 and 19. So that's what we're doing. That's why we also have to count the number of ways you chose those 2 losing balls. There's a lot of different options of choosing the losing balls. So I'm going to do the same thing with the mega ball. Okay, there's 1 winning mega ball, so it says you chose that one. But technically, now this is 1 and the other one's 1, so we kind of really didn't have to put it, but just to match our format, then that means there's 45 losing gold balls, and you didn't choose any. Right? So this is what I wanted to be clear about on all our other examples. If I only chose 3 winning balls, I also have to count the number of ways I chose those losing balls. Remember, we have to, when we put this in our calculator, we've got to put parentheses around numerators and denominators. All right? So don't forget your parentheses, and I'm just going to plug that into my calculator. And I'm going to do them individually because I think your homework always asks you to leave this as a fraction. So we'll talk about simplifying this ridiculous fraction that our calculator won't do for us. So 5 choose 3 times 51 choose, well, no, not 21, 51 choose 2 is 12,750. And the denominator is 56 choose 5 times 46 which gives us 1,757 1,1536. Okay, and I can tell probably the easiest way, just since, we're not in a heavy algebra class, to simplify this fraction. If I try to use my calculator to simplify it, it's just going to keep giving me that decimal equivalent. It's not really going to simplify it. So I can think about, I can tell they're both even. So I'm just going to go through and divide them by 2. Anything I notice that they have in common. 8, 7 on the denominator. I did it first since it was on my calculator. 8, 5, 5, 7, 6, 8. Now I'm going to take the 12,750 and divide it by 2 and get 6375. I notice they're no longer divisible by 2, so I might try 3. Oh yeah, 6375 is divisible by 3. So let's see if this denominator is. 8, 7, 8, 5, 5, 7, 6, 8. Oh, yes, it is. So 2, 9, 2, 8, 5, 2, 5, 6. Now I could tell over here they weren't divisible by 2 again, but maybe I can't tell if they're divisible by 3 again, so I'm going to just divide it by 3 again. Hey, that denominator is divisible by 3. 976, 1752. Let's check the numerator. Oh no, it's 708.33333. So okay, I'm done checking 3's. I know this one's not divisible by 4, right? Because it'd have to be even to be divisible by 4. This one's not divisible by 5. This is not divisible by 6 because it'd have to be even. Maybe I'll check 7. 21, 25 divided by 7. Nope, 303 point dot 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 dot. So not divisible by 8. And I've already checked it's not divisible by another 3, so it can't be divisible by 9. The last thing I might want to check is 11. And then when I've checked, several numbers, I just have to, for this class, I'm going to assume that that's completely simplified. Okay, here's another one. A box contains 25 transistors, 6 of which are defective. If 6 are selected at random, find the probability that all are defective. So the probability of 6 defective ones. First of all, I have to decide if it's a permutation or a combination. And this says I got a box of 25 transistors. I'm going to reach in and grab 6. The order doesn't matter that I grab them in. Once I have 6 of them, I'm going to examine them. It doesn't matter, again, the order. If I look at the first one that I grabbed first or the last one that I grabbed and look at it first, it's still the same 6 I'm looking at. So it's a combination. So the denominator, if there's 25 transistors and I'm going to choose 6 of them, right? Reach in and grab 6. That's 25, choose 6. Now the numerator is about the event which they're asking me about find a probability that all are defective. So those 6 that I've chosen have to come from the 6 defective ones. So that's 6, choose 6. Or, and, I guess I should say, and on my second thought, now since I've already chosen all 6 of mine, that means I'm going to choose 0 out of the other group. But still, just to keep in mind that format, that means, hey, if 6 are defective, there's 19 good ones. But I'm going to choose 0 of those. Actually, both of these are 1, right? There's only one way you can get those 6 defective ones. That's if you pick up the 6 defective ones. There's only one way that can happen. So I know that numerator is 1. If I don't catch that, I plug that in my calculator and see what it is. And now I just need to see the denominator, which is going to be 25, choose 6, right? 25, choose 6, which is 177,100. Now it asks me to find the probability that none are defective. Well, the denominator is the same, right? It's all of the ways you can reach in there and grab 6. But this time, if I don't want any defective, then that means out of those defective ones, I'm choosing 0. And all 6 of them are coming from the 19 good ones. Again, technically this is 1, so I could have just had the 19 choose 6, but I had to recognize that that's 1. We always have to count both items. Okay, so this is 19 choose 6, and we already know that the 25 choose 6. We've calculated that. So let's just do now 19 choose 6, which is 27,132. Again, this is probably a little too large for our calculator to simplify for us, but I notice they're both even, so I'm going to divide both of them by 2. 13,566 and 88,550. Oh, they're both even again. I'm dividing them by 2 again. 44,275. $6,783. All right, they're not even anymore. Maybe I'll try 3. Oh, that top number is divisible by 3. Let's look at the bottom one. Nope, got a decimal. It's not divisible by 3. Okay, and it can't be divisible by 4. They're not even. This one's not divisible by 5. It's not divisible by 6. We better try 7. Okay, this one's divisible by 7. Oh, and so is the denominator. Okay, maybe I better try 7 again. Nope, not divisible by 7. They're not divisible by 8, I can tell, or 9 because 3 didn't work. So maybe, what about 11? Okay, this one's divisible by 11. Oh, but the numerator's not. So once again, I'm just going to, at this point, assume, hope, that that's completely simplified. Ah, no. Okay, guys, sorry, had a snafu there, but I'm going to keep going because we're nearly through. We only had one page left, so I'm just going to go back to where we were, hopefully. Okay, sorry about that. Alrighty. A city council consists of 6 Democrats and 4 Republicans. If a committee of 3 people is selected, find the probability of selecting 1 Democrat and 2 Republicans. All right, so we want the probability of 1 Dem and 2 Republicans. First, I have to decide permutation or combination. It's just a committee, so it's a combination. The order you're chosen to serve on a committee doesn't matter. It's not like choosing a president, vice president, secretary, where the order does matter. So our denominator is, let's see, there's 10 people altogether, and we're going to choose 3 of them. All right? 10 choose 3. Okay? And the numerator says 1 Democrat and 2 Republicans. So there's 6 Democrats that I'm going to choose that 1 from, and there's 4 Republicans that I'm going to choose that 2 from. Notice we've accounted for both sections, right? I've got my 10 here, my 3, everything's good. So in the denominator, we have 10, let's see, choose 3, so that's 120. And in the numerator, we have 6, choose 1, times 4, choose 2, which gives us 72. Now this one our calculator will simplify for us, right? Find your button on your calculator that simplifies things, although it also might be easy enough to do just without the calculator. Okay, so I know they're both divisible by what, 6, right? 6 times 12 is 72, and this would be 20. So now they're both divisible by 4, so 3/5. Okay. A poker hand consists of 5 cards. Find the total number of possible 5-card poker hands. Okay. Now, it's asking me the total number. Didn't ask me the probability, right? Pay attention to that. Is it asking the number or the probability? Okay, permutation or combination. If you're dealt an ace and a king, does it matter if you're dealt the king first or the ace first? Nope. Order doesn't matter. You'd have the same hand, right? When you pick them up, you're going to have an ace and a king. So order doesn't matter. That means there's 52 cards, and I'm going to choose 5 of them. So 52, choose 5 is 2, 5, 9, 8, 9, 6, 0. A diamond flush is a 5-card hand consisting of all diamonds. Find the number of possible diamond flushes. Okay, so diamonds, there's only 13 diamonds, right? There's 13 of each suit. So I want my 5 cards to come out of all diamonds. So 13 choose 5 is 1287. Find the probability of being dealt a diamond flush. Look, I don't know why that says 1, 1, 1. Okay. So the probability that you get a diamond flush is the total number of ways you can get a 5-card hand and the total number of ways all 5 of them can be diamonds. They're not divisible. They're not both divisible by 2. Let's see if 1287 is divisible by 3. It is. Let's see if 2,598,960 is divisible by 2. Not 2, sorry. 3. It is. No. Let's see if it's divisible by 3 again. The numerator certainly is. But the denominator's not. Okay, this one's not divisible by 4 or 5 or 6. Maybe I should try 7. Nope, it's not divisible by 7. I can tell not 8. 9 because it wasn't divisible by 3 again. It's not divisible by 10. Maybe we'll try 11. It is divisible by 11. What's happening? Give me my pen. Okay. Let's try the denominator. See if it's divisible by 11. It is not. So once again, I'm going to hope that I've completely simplified that. Okay, if you're dealt 4 cards from a shuffled 52-card deck, find the probability of getting 2 queens and 2 kings. So the probability of 2 queens and 2 kings. We just said that being dealt cards is a combination. The order you're dealt them in does not matter. You'll still have the same hand when you pick them up. Okay, so that's 52. Choose 4 this time because we're dealt 4 cards. Now we want to know the probability of getting 2 queens and 2 kings. Well, there's 4 queens and we want to choose 2 of them. And there's 4 kings and we want to choose 2 of them. Now technically that's enough information, but just as a thought, make sure really what we're saying is we got to account for all the possible cards, right? Here's 8 cards. So if there's 52 cards, that leaves 44 cards left, but I'm going to choose 0 of those, which this is 1, right? But again, just this is a thought consideration. I don't really have to have it on there because it's 1, but just to make me recognize that I look at all options, you know, I've got the kings, the queens, all the other cards, and how many I get out of it. So let's see what our numerator is. 52, choose 4. Is 270,725. And on the top, I've got 4 choose 2 times 4 choose 2. Which is 36. Oh, I lost my thing again. I don't know why that keeps happening. Okay, 36. Okay, and I'll leave that to you to try to simplify. You know, the only number, this is a pretty easy one because the only numbers that divide into 36 are like 9, 4, 12, 3, 2, right? So check those numbers down here. And then go have fun. And I will see you next time.